One, near and dear to my heart. It's taking a look at the dedicated security components, a FIPS module in the CC world. And so many of you know that the long road that we took with DSC in the CC, but now really looking, because I've actually had some conversations with some folks recently, and even with Margaret, those of you who are listening to Margaret earlier, Margaret Salter, about the need for a crypto PP module. So maybe this is what we can guide Margaret on that side. So again, let's get started. We have both Brian Wood, Program Manager for Security Certifications at Google, and Joachim, I can never pronounce your last name. Joachim, I'm sorry. Vandersmissen. That's right. Deputy CC Lab Manager at atsec. Will take us through again the dedicated security component, a FIPS module in the CC world. Take it away, guys.
All right, thank you. Okay. All right, so I'm going to do the first part, and he's going to do the important part. So our basic agenda, we're just going to kind of outline what we're going to do, look kind of like this. Talk about what is this protection profile, where is it coming from, and then we'll get into how it compares to FIPS. So I'll get going so we can spend time on the important stuff. So this is always a question here, is that I don't know how many people here actually do common criteria. They might have heard the words, might swear at them at times. But basically, common criteria, you might hear NIAP or BSI and such. Those are just the people who do the certifications, kind of like NIST. But it's just a language for how to write security requirements. So you could use them for any type of an evaluation. Technically, you could write common criteria to do what FIPS does. I mean, there's no real reason why you couldn't. It's just nobody does that. FIPS is pretty good on its own. But that flexibility lets you then be able to evaluate things, different types of products, different types of scenarios, and it encompasses both the requirements and the evaluation methodology. So you can basically lay out what you want to evaluate and how you want to evaluate it. Now, protection profiles, so we're talking about the DSC PP. The PP protection profile is kind of like the set of requirements that target my product. So I usually think about that as kind of like the RFP as to what I'm going to do. The PP could also be a good example, actually, if I looked at it in FIPS, would be something like the level 1 requirements for a module. So it tells me I have to do a certain number of things, and I have security requirements written out for those. And basically, in a common criteria terms, that's kind of like a PP. The way I usually explain it as an RFP is that, hey, this is my security requirements I want you to meet, and then you're going to tell me how you meet them, and then that's essentially your evaluation evidence that you're going to provide. And here, as I mentioned, NIAP, that's the National Information Assurance Partnership. The people in the United States who do the evaluation. They are one of 31 current countries that accept common criteria evaluations. So it does have a little more broad acceptance compared to FIPS. So what is DSC? The ITC? ITC is a common criteria construct for vendors, schemes, labs, and whoever is interested to come together to write security requirement documents targeting to a product. So DSC, Shawn used to be the chair, then he passed it on to me. So we started in 2016, and in 2020 released version 1.0. As of September 6th, we actually published a public draft. We're in the last stages for publication, which we're expecting to do by the end of next month. That link, which I can give you if you're interested in knowing, please feel free to take a look if you want to see the latest version or if you want to provide any comments on it. So what is a dedicated security component? Well, that's not super clear. Now, I say that in a good way, though. What is a FIPS module, right? It can be anything that I want it to be. It could be software, it could be hardware, it could be some combination of firmware, hybrid. There's all kinds of things I can do. The DSC is more so designed to provide a set of security functions. How exactly you present those functions from hardware and software is kind of up to you. The idea is that you would then establish your scope. You have a bunch of requirements to meet. You put them together, and there you go. There's your product. So we have some core common use cases, secure data storage like a key store, a lot of cryptographic services, so not just the algorithms, but how you use them in terms of their exposed functionality. And then kind of a secure layer for connectivity between services. So if I have different services on a device that are that all need to work together, I can use this to connect those. So generally, we don't assume that a DSC is going to be a discrete component, but for the rest of this presentation, we're actually going to utilize a secure element as an example. And that's just for simplicity in talking, not because we actually ever expect anybody to use this requirements for a secure element, mainly because it has its own PPs for PP84, which is usually what everybody does for that. So, but we figure that everybody knows what a secure element is, and so it's a good thing to use as an example. So the CPP has obviously cryptographic functions. One thing to note is that because it is not US-Canadian focused, it is actually written with international algorithms. So we have a lot of algorithms, a couple from Europe, some from Japan, some from Korea that are all in there and could be accepted. Doesn't mean you have to use them, but you can certainly certify the DSC utilizing them. Obviously, NIST algorithms are all accepted as well. Then we have some other things about integrity. So how do you verify that the DSC is correctly operating? How we're protecting some of the data, input, output, as well as internal roles and responsibilities of who can access and how you can access the data, and then, of course, some of the management of the data itself. Now, with that, I'm going to turn this over to Joachim.
Thank you, Brian. So I would like to talk a bit about how FIPS and the DSCPP relate to each other, the requirements, how they are similar, and maybe how they are different. And as Brian mentioned, we'll be using an example, a secure element, as a potential evaluation candidate under the DSC CPP. And in this case, it will be some kind of hardware component with additional firmware that is embedded in an SoC. And we will assume that it is validated under FIPS 140-3 as a level 3 module. So that means it uses FIPS-approved algorithms, it has some kind of trusted channel or key wrapping to input and output keys. It implements authentication, probably identity-based authentication then. It has physical security and maybe side channel protection, EFP or EFT protection. And if the firmware is there, it has some kind of signature verification or integrity test. And of course, the cryptographic algorithms are self-tested. So this is kind of our setup, what we would look into when we look at the requirements for DSC. Before we talk about actual requirements, before we go deep into the requirements, I'd first like to clear up some terminology, as Brian did, because a lot of you are probably familiar with FIPS, but not with the DSC at all. So in FIPS, we are talking about the cryptographic module, which is what is being validated. And the common criteria, this is called the target of evaluation, or short, the TOE. Conceptually, it's the same thing, but it's just a different name. Similarly, the keying material in FIPS, those are the sensitive security parameters, or SSPs, which are split up in the private keys, the CSPs, and the public keys, or the PSPs. On the other hand, the DSC introduces the concept of security data objects, SDOs, and security data elements, SDEs. And the SDEs would be your keying material, whereas the SDOs could be one or more SDEs that are combined with some metadata or binding material. For example, it could indicate ownership information as to who is allowed to access these SDEs within the SDO. Similar to FIPS, of course, there's many operations that you can do using that key material. So there's the whole life cycle of entry, generation, storage, using it in approved services, zeroization, output in FIPS. And these have specific terms in the DSC CPP. So you can see those 7 services there. They all start with a P. and that's parse and provision. That would be kind of your entry and generation. Then protection of the SSPs stored in the DSC, processing to use them in cryptographic services, the proof service, which is actually an attestation service where the DSC CPP has first-class support for attestation. It's coming to FIPS in an upcoming version, but right now FIPS does not have that support just yet. Then there's purge and propagate, which are zeroization and output of SSPs, or SDEs in this case, respectively. So the terminology is a little bit different, but the actual underlying concepts are the same. As Brian mentioned, a FIPS module can be software, firmware, or hardware, or some kind of combination of those. At level 1 and 2, you can do software and firmware standalone. At level 3 and 4, you need to involve some hardware components. On the other hand, the DSC is defined as a hardware component or some kind of hardware and associated firmware. So there is a slight restriction there. If you do DSC, it needs to be some kind of hardware or hardware firmware. And this component needs to be embedded in a larger system by definition as it is component, whereas FIPS modules can exist standalone. There's also some differences in terms of the requirements, the wording. Those are mainly process related, not really technical. The main interesting difference might be the difference between areas in FIPS versus assurance classes in DSC. So the assurance classes would be kind of a grouping of requirements. And speaking about assurance classes, we'll look at our first technical assurance class, which is cryptography, probably the most important assurance class for both FIPS modules and the dedicated security component. As Brian mentioned, the DSC has multiple algorithms that are allowed, not necessarily just the NIST algorithms, but also international algorithms. If we're looking at NIAP, however, which is the United States scheme, you will be restricted to the NIST or FIPS-approved algorithms. Each scheme under which you validate, even though the DSC PP might be validated under different schemes, they might impose rules on which algorithms they like or don't like, and NIAP likes the NIST algorithms, so you would be restricted to those. But if you have a FIPS module, that shouldn't be any problem because you should be using the NIST algorithms anyway. There's some small exceptions like TripleDIS, SHA-1, DSA that NIAP doesn't allow generally, whereas NIST, or I guess CMVP, is phasing them out right now. If you implement these NIST algorithms, NIAP requires that you do ACVP testing. However, if you have a FIPS module, again, you should already have done this ACVP testing because it is a prerequisite for the FIPS evaluation. So in that sense, there's no additional requirements there for the cryptography. On the other hand, the DSCPP and NIAP have specific rules about entropy sources and entropy. Luckily, NIAP actually released quite recently a rule that if you have an entropy source validation or ESV certificate, this can be used as evidence for the entropy rate in your DSC evaluation. So that means if you have done a FIPS validation and you obtained an ESV certificate as part of that evaluation, then you can simply reuse that certificate. There's a very lightweight entropy assessment report that is still included that will basically describe how this ESV certificate relates to the DSC. But other than that, there are no additional requirements, and the lab might be able to help out with that EAR. So that being said, ACVP and ESV cover the cryptographic related requirements in the DSC almost completely. So there's almost a one-to-one mapping there. Next up is the key management. So I spoke about this briefly, about these P services, and the actual requirements that are related to these services are, again, very, very similar to FIPS. For example, the storage of SDEs, in this case, needs to be controlled to the owner that actually owns this SDE. As you remember, each SDE is part of an SDO, and the SDO has ownership information. So the DSC must restrict access to that SDE or SDO to the owner. And similarly, the DSC must enforce confidentiality and integrity, but this should already be provided by your FIPS module. These are not new requirements. FIPS has these requirements too. For output and entry of SDEs and SDOs, the requirements are basically identical to FIPS. If you are importing or outputting a key material, it needs to be wrapped using a different key, or it needs to use a trusted path, being either a physically trusted path or some kind of cryptographically protected channel. Finally, the DSC needs to zeroize the SDEs or SDOs if they are no longer required. This can be done by overwriting them with zeros, or if they are kept in volatile memory, just turning off the DSC or relying on some kind of garbage collection. Again, these requirements are basically identical to FIPS. So if you have a FIPS module at, say, level 3 that meets the FIPS requirements, these requirements should not be an issue at all. Then we come to identification and authentication. In this case, the DSC is actually a little bit more permissive, and I would say easier to use than FIPS. In FIPS, authentication is generally on a higher level, either a service level or some kind of module level, where the operator authenticates to the module, and it uses the module checks this authentication to perform the services. On the other hand, in DSC, the authentication is performed on a key level or SDO level. That means if the operator is authenticated to use that specific key, then it can be used. Or if the attributes say that the operator can use that key, then that's fine. So this is a more granular level, which allows the vendor more control over how to configure this authentication. Moreover, DSCPP generally has more permissive authentication methods, whereas FIPS has SP800-140E, which may or may not be normative depending on your type of module. The DSC allows you to simply use industry standard methods. And this also means that if you have externally provided authentication material, the DSC has no control over it, so there's no rules around it. If you do generate authentication material internally, there are some rules. For example, you need to use the DRBG and the entropy source that are part of the DSC, of course. The DSC does require authentication for management functions to manage the tow specifically. Finally, there's the area of operational security. This would be like the security of the tow itself, or the security of the dedicated security component. And there are some requirements here that, again, match very closely to the FIPS requirements. For example, fault injection. In that case, if the DSC does detect faults being injected, it must preserve the secure state in some way. The way this is preserved is defined by the vendor. That could be something like shutting down the DSC to prevent any further injections. If the DSC contains firmware, then if this is mutable, it needs to be integrity checked when it's installed and when updates happen, and there needs to be some kind of rollback protection. However, this is all generally industry standard. The industry already performs these checks, so that should not be an issue. The DSC also needs to provide protection against physical attacks, and in this case, the requirements are actually taken directly from the FIPS standard, the EFP or EFT prevention. That means environmental failure protection or environmental failure testing. Those attacks are exactly the same as FIPS. So if you meet the FIPS requirements in that area, then you should be able to meet the requirements in DSC. There are some other smaller requirements. For example, the DSC must maintain some kind of root of trust for confidentiality or maybe for attestation purposes. It needs to implement prevention of replay attacks for authentication. And of course, if you are validating on the NIAP, you will have self-tests for the cryptographic algorithms, as well as an integrity test on the code and the data that's part of your DSC. These requirements are very similar to FIPS, the self-tests, and the physical security requirements. With those technical differences out of the way, I'd also like to talk a bit about the process differences. As Brian mentioned, this is common criteria, which means it's a completely different process from FIPS. If we are talking about NIAP, which I will focus on because I'm more familiar with NIAP and it's the United States-based scheme, then the process can be divided in roughly 3 stages. The first stage is prior to the evaluation of your product. If we're talking about a dedicated security component or DSCPP, you would select this PP, and then you would work with the lab to draft the evidence that is required for the submission. That would be the security target, which is similar to a security policy in FIPS, but there's more to it. The entropy assessment report. Hopefully, if you have a FIPS module, you just have an ESV certificate. In that case, the entropy assessment report would simply refer to the ESV certificate, and that wouldn't be much work. And then the key management document, which describes how your keys are used. Also part of the pre-evaluation stage would be pre-testing, because NIAP has a very strict time limit on how long evaluations are allowed to take. Labs generally perform some pre-testing on the TOE to make sure that it can actually meet the requirements. Because if you don't meet the requirements and you're already in evaluation, then you could have a big problem once that deadline starts creeping up. But let's say all of this goes well, then the check-in process starts with NIAP. That means the lab and the vendor submit what's called the check-in package, and the evaluation officially starts. And what happens first is NIAP will assign the validators, which are actually the reviewers of the project. So this is very useful compared to CMVP, because in this case, you have someone to contact if there are problems or maybe uncertainties, or there are some questions about your evaluation process while you're looking at the TOE. You can contact the reviewers or validators directly and try to figure out a solution. Secondly, NIAP does not charge any fees compared to CMVP. Of course, if you're using a CC lab, they will probably charge a fee, but there won't be any fee from NIAP. And NIAP also does not require any code review. And these PPs that NIAP has are actually written in such a way to try to avoid code review as much as possible. All the evaluation activities should be able to be met using functional testing only. Once this process starts, let's say your TOE is in evaluation, then the actual official functional testing starts. Potentially ACVP testing, but if you have a FIPS module, that part should already be taken care of, and some more evidence gathering by the lab. And this will also include drafting the documentation or reviewing the documentation to be submitted to NIAP. All of this needs to end within 180 days. As I mentioned, NIAP enforces this limit, so the whole evaluation process, including the review by the validator, needs to be completed within 180 days. If this is not completed, then the validation does not succeed. So that means that the labs and the validators and NIAP have an incentive to get the evaluation finished within this time period. Compared to the CMVP queue, this might be a little fast, a little more expeditious, and maybe an advantage if you are looking to evaluate some kind of secure component. After the DSC has been evaluated, there is a 2-year period in which the certificate is active. In that case, it would be a certificate under the dedicated security component protection profile. And in case that this certificate will sunset, it is possible to perform what's called assurance maintenance. If your product did not change, then it should be relatively painless to go through the assurance maintenance process and renew the certificate. With that being said, I would just like to emphasize that if you have a FIPS module at, say, level 3, a hardware module, it should be very easy, or at least from a technical perspective, there should not be any changes required to the FIPS module to validate under DSC. The DSC requirements are very closely related to FIPS, and there should not be any problem from a technical perspective. From a process perspective, you will likely need to gather more evidence. You will maybe need to draft more evidence, but technically speaking, there should not be any changes. And because the NIAP validation process is different from CMVP, I think it is probably better in some ways. For example, the assignment of the validators at the start of the process, the time limit, this can ensure that the actual evaluation of your product is faster than what we are currently seeing in the FIPS queue. With that, I'd like to pass it over to Brian again for some final remarks.
Thank you. So we'd like to emphasize that we see common criteria and NIST are complementary. They're not really in competition with each other. I mean, in some ways, they kind of are. But overall, NIAP, at least in the United States, largely just kind of says, all right, if you've got cryptography, make sure you've talked to NIST first. So whether that's module or just algorithm, this is kind of up to you. Their minimum requirement is algorithms, algorithm validations. And obviously, the way that the DSC CPP has been written is basically to align the functionality. A lot of the differences really come down to looking at, FIPS really looks at mostly just the crypto and making sure that you're implementing that correctly, and doesn't really pay as much attention to why are you doing the crypto, what are you doing with the crypto, how are you using the crypto. And the DSC's common criteria in general, and DSC in particular, is really trying to provide you that framework of, well, why are you doing these things, and what are the things I want you to be able to do with the crypto that you're including in here. So they really, that really does kind of, they complement each other. So if you're looking at just doing the module, that's great, and then you can kind of reuse that module in a bunch of different places. DSC is really intended as something that provides a whole set of services beyond just crypto for you. And I mentioned this before, but I'll just want to say it again. The ITC that generates this is essentially an open group. So we have biweekly calls. We discuss the changes, what are the way we think this thing should be written, why it should be written certain ways, and that includes both the requirements themselves and the evaluation activities that go with those requirements. So this is all essentially, it's more like CMUF, except that instead of contributing to NIST, you are NIST. You know, we're writing the entire thing. And so if you want to participate, happy to have you help. As I said, we have a current draft at the moment that is almost ready for publication. So thank you.
And unfortunately, we're right at the end, but if someone had one quick question, we could do one, and then we'd need to transition on to our next discussion. If not, again, join me in thanking both Brian and Joachim for a very good discussion. And I don't know if you remember, Seamus did another one up in Ottawa. We were just talking about that. And so let me turn this over to Seamus Mulready. A funny thing happened on the way to the test lab.
Hi folks, I'm Seamus, and I'm with Lightship Security, North America's coolest cybersecurity certification lab. Let's just get something out of the way. This is a test of the unamplified broadcast system. Can everybody hear me? Yes. All right, great. For the next little bit, I'm going to take you out of Tech Talk land and into the theater. And in the theater, there are no microphones. So you can help me by just being a little bit extra quiet for the next 15 to 20 minutes. And in exchange, I promise you'll enjoy the presentation just a little bit more. Thankfully, I spent a decade of my life mastering the craft of being really, really loud and earned a PhD in loudness. That's a lie. I'm an actor, you see. But like most stage actors, I was only ever in it for the money. I always knew deep down in my heart that I wanted to be a cybersecurity certifications tester, just like my father and his father before him. That might also have been a lie. For the next little bit, I am also a CMVP reviewer, guardian of the federal infrastructure, and last line of defense against those who would foolishly roll crypto on their own like it was 1995. But that's not all. I am also a product vendor, providing the critical infrastructure that keeps the federal government running and chasing those sweet, sweet government contracts. Today, I'm going to give you all a little taste of this weird multi-partner dance that we do through the FIPS validation process. Because in FIPS, it takes 3 to tango. Maestro, if you would be so kind. I've always hated the way people drive. Driving to work, not We've reached the forever traffic. I think we're going to be here for a little while.
Good morning, listeners. This is your daily traffic report. My condolences to all those poor people out on the roads today as serious traffic jams caused by the construction of the new Highway 3 continue. Get comfortable, folks, because we expect these major delays to persist until the...
Well, this isn't working. I mean, look at this. One road, no shortcuts, and I cannot remember the last time I have seen anybody move. I think it's about time we try something different.
Line BR1 to validation.
The next station is Telecom Center U9.
The king material derived from a given key derivation key could subsequently be used as one or more key derivation keys to derive still more key derivation keys, derive key derivation, key derivation.
自動運転中です。緊急の場合、その他お困りの際はお近くのインターホンでお知らせください。また、道路の
Hello, sir, and welcome to Coffee Made Virtually Perfect, where we do the thing which is our name. Can I take your order, please?
Oh, I'm sorry, sir. We've actually moved to a closed book ordering system.
Why? Look, I've been ordering coffee from you. You know I can.
Well, we here at Coffee Made Virtually Perfect strongly believe that our customers should have memorized all of our delicious offerings before placing an order.
Well, that certainly would be a lot easier to do if the menu wasn't half coffee jargon.
It's Italian, sir.
Well, then I'll have Americano espresso, some alla carte.
Great! Can I get you anything else today, sir?
Yeah, I'm also an online and
By all means. Can I have the order number, please?
understand. Believe me, I fully understand this is critical path. With all due respect, I don't really think this is a tomorrow problem. Because the one person who's been maintaining all of the undocumented code at the bottom of this, that kind of just leave it with me, okay? We'll get this sorted. Yeah, thank you. Ciao. Hey, buddy, you there?
Good morning. How is everything over there at Vendor Inc.?
Same disaster, different day.
Great. Listen, I'm at the coffee shop. What was your order number?
Order number. Hey, is the barista there that looks exactly like you?
He does not.
Okay, well, order number.
1,
1,
2,
2,
3,
3,
3,
4,
4,
4,
5.
5.
5. So that's 1, 2, 3, 4, 5. It's amazing. I've got the same combination on my luggage. Well, let's see here. I'm sorry, sir. Your order's not quite ready yet, but it should be prepared shortly.
It's not ready. It should be prepared.
No, I heard you. Thank you, though.
That wasn't me, that was the barista.
Oh, you guys sound the same, too. Honestly, I can't believe you don't see it. I'll be honest. From my perspective, I can't tell where the one of you ends and the other begins. Look, I gotta drop, okay? I'll see you soon. Most complicated cup of coffee ever.
Hey, is this gonna be a while? I've got to stop by the post office, too.
We're currently preparing orders made in the May 2023 timeframe.
Well, I guess let's see what's on the docket for today. A new submission. Looks right. Sounds good too. Oh no. A tangled mess of spaghetti. A tangled mess of spaghetti again. These days I feel like half of what we get is, well, you get the idea. I don't understand. I mean, I thought the instructions were pretty clear. We made them flowcharts to follow. We made them that great checklist, too. And yet, and still, spaghetti. If only there was some way to keep all this spaghetti from landing on my desk in the first place.
I am Auto-Resolve Unit AR140-3, the world's most advanced submission processing system. None shall pass! Unless formatted per relevant guidance.
Here goes.
Improper naming convention!
Oh, yeah, okay, no, that's my fault. Let's try that again.
Superfluous attachment detected.
Yeah. I got this.
Insufficient documentation.
Come on, man.
Unspecified error.
Unspecified error?
You will never defeat auto-resolve.
Oh, eh?
Your submission has been successfully processed.
Well, that's a win. We take those. Now just one more submission. I've just got to remember how to do this. What did they say about that checkbox? I think it was in an email somewhere. What's the worst that can happen?
Your submission has been successfully processed.
Oh, I just had the strangest dream. Two submissions in one day. That's ambitious. Well, it does look right. And it doesn't feel at all like spaghetti. They checked the checkbox. They checked the unlabeled checkbox and there's nothing to check. Wishful thinking, I guess. I'm starting to think it's going to take more than a checklist and some basic automation to untangle this mess.
11th floor.
We've made it, finally. Not to the end, mind you, just to the test lab. But now that we're here, we can finally get some work done, right? I'll be honest. I'm really just happy to put all that behind me. Hey, that's me! And some of you too! I know some of you are here. it's been great to meet all of you too. My creative partner. I guess questions, if there's questions.
I think we need more of these, don't we? Any questions for Seamus? I guess it all got across, right? No explanation needed? Okay. If not, we just need a couple minutes to move things back, and then at the bottom of the hour, we'll get going with our next session. Okay, again, last session, and we're going to get into some Quantropi entropy discussions here. As always, we're trying to end before the end of the session so that we have time for questions. I know we ran out on some of the previous ones, but so our next session here is with Michael Redding, the CTO of Quantropi, and this is all on Quantropi entropy, emerging uses for advancing threats. So join me in welcoming Michael Redding.
All right, well, thank you for having me. I find myself in the intriguing position that I find myself between a very entertaining piece of crypto theater and the recess for the day. So I'll do my best to entertain to the level of maybe shadow puppets, because that's about as far as my skill set goes. And to some degree, this is kind of a wraparound topic. I think the entropy track was full, and so they said, well, let's have this topic in this slot because it was available. So here I am, and here you are. So thank you for joining me. And it was given a pretty wide range on what we could talk about today. And so the thinking was to chat a little bit about a wave of technology that's coming, and with regards to quantum technology, especially around quantum entropy itself, and to focus a little bit on the threat vectors in particular to entropy, talk a little bit about sources of quantum entropy, but then also bring it home a little bit in terms of some of the use cases we're starting to see people experiment with, test out for using quantum entropy to solve near-term risks to security. So it's a bit of a survey course, but hopefully it goes from threat to response to use case in a way that is at least interesting and worthwhile. So that's what we're going to talk about, and I actually cribbed this unintentionally from the first speaker in the entropy track this morning. But everyone always says, well, if you have bad entropy, it increases your chance to break encryption. And I put break in quotes because you're not attacking the underlying algorithm, you're guessing the password, right? You're turning the lock because you're able to either forge or know the key. And so breaking is not quite the right word. You're not even picking the lock. You're basically replicating the key and the lock pops open of its own free will. But it's still an important focus, because I would say that, year over year, I went to the last ICMC in Ottawa, and there was a sub-track around post-quantum cryptography, and I would say at this year's event, vast, number one topic by volume is no doubt post-quantum cryptography, thanks to NIST delivering the new standards. That's fantastic. And a lot of the RNG conversation is, again, very traditional talks, but what's interesting is the threat vector on entropy is actually accelerating, but the villain in the story is not a quantum computer per se. It's actually, it's, I guess, somewhat in this case, evil twin, machine learning and artificial intelligence. Because in the entropy and random number community, there's always an ongoing healthy debate about how do I know something is random? How can I prove that it's truly random and that there is no biases? when in fact, with AI and machine learning, I can actually detect and prove the exact opposite, that it isn't random and that it does have biases, and because of that, I'm off to the races in doing something unsavory. And so it's an interesting thing, and then with post-quantum cryptography, we're trying to protect against quantum. With quantum entropy, we're trying to use quantum technology for protection. So a little bit inverses, but wanted to bring that forward. And so a quick journey in the last few years, these are somewhat chronologically arranged, but a number of studies have gone out to show that when you start with a bad foundation, bad things happen. This one is a little over a decade old, and that's why you see DSA appearing a bit in the statistical results. Hopefully, if you reran this particular survey, and this was over 12 million TLS and SSH servers, so this is looking at network devices exposed to the internet, hopefully you'd see much fewer instances of DSA. Hopefully none, but these things happen. But again, it's starting to show you that a non-zero percentage are based on a bad random starting point. And jump it ahead, and here was a study done by Keyfactor, and there they found that in IoT, about 1 in every 172 certificates were vulnerable, again, because they started with bad random. And this one is super interesting because here, a study was looking at AES encryption keys, and everyone always worries about the length. Is it 256? 256 is better than 128. But turns out they showed in this study that if you had less than 220 bits of true randomness in your 256 bits, you might as well not bother. You can be compromised in effectively real time. And to put that in perspective, when you start to look at a random number source, one of the things they provide is the entropy rate, right? Which is the number of entry bits over total bits, right? Simple math, or division, even I can do it. But what's interesting about that is NIST doesn't set a floor during a certification. They just say you have to specify it, and you have to be able to prove you can at least achieve that rate. And so what's interesting is that this study came back and said, if your entropy source is less than 0.85, and I will not cast aspersions on anyone in particular, but there are plenty of commercial products out there with a number, including a gentleman talked today about an Intel product where Intel proudly says it's 0.6. According to this, that 0.6 entropy rate source would not be giving you keys sufficient to protect AES encrypted traffic. So it starts to give you a flavor for the concerns. This was another study that, again, using machine learning, read the internet. Instead of doing 12 million, in this case, they did over 250 million certificates, and they found a whopping percentage, about 36%, that had, of a certain class, had duplicate X509 certificates. That means people had 113,000 friends or clones of themselves. And if one of those devices is at the front door of the Pentagon, and I go to Army Surplus and buy its twin, I'm in the network. And so a great example of a large-scale propagation. To put a financial figure on it, this came out last year, Randstorm, where a Bitcoin wallet had in its implementation of a Java class a bad random number. And so from 2000, I think it was 11 to 2015, everybody who used that wallet made a bad wallet such that if it's cold, it's still protected. But if it ever touches the internet, basically you can scoop the coins out of it. And at the last time they checked, when this report came out, that day the value was between 1.2 and 2.1 billion dollars waiting to be stolen in real time as soon as any of those wallets. And you can imagine people are hovering, waiting to see those guys appear. And last but not least, and the most recent, this is work done by a research team headed up by a professor out of Duke that also works with Meta. This was actually at the August 6th NIST seminar on post-quantum cryptography, and it was talking about benchmarking attacks on learning with errors. So there the research team is trying to use machine learning to go after Kyber, or now MLChem itself. But a funny thing happened on the way to MLChem was they found out that if it has bad random, they don't need to attack the lattice, they can just solve it. And they found two completely different attack mechanisms that basically said bad random equals I win. And so that just shows you that even the newest standards coming out of NIST, again, start with something bad, you end up with something bad. And again, this may seem like common sense, but you can't point to enough that the tools to do these reports, it went from 12 million 10 years ago to 250 million. You can scan everything and anything, so you can't achieve security through obscurity. So ultimately, when we get to it, it comes down to therefore, okay, what am I gonna do about this? I've got potentially two approaches. One is hardware sources of random and software sources of random. This is what we know and love. And the question becomes how do we translate that now into a quantum upgrade? And so with hardware, the important thing is that the shift in the physical process at the heart of it is now intended to be some kind of actual quantum process, some kind of modality that is ideally provably a quantum phenomena. And so it has things like superposition and other attributes. And in fact, NIST and others have done a lot of great work to start to develop tests like the Bell test and the Bell test without loopholes to say, can we confirm that this source is behaving in a truly unpredictable quantum manner? Because that's thought as if the universe and quantum is truly unpredictable, then we've just upgraded the root of all of our random number needs. And so this is an eye chart, but like any other emerging technology space, there's a taxonomy. And so other folks, you can follow the link, folks are now starting to break it out, look at the different techniques, but there are a few primary modalities that people are exploring, but as always with any technology, there are many more to come, and I just thought I'd highlight a few. I would say one of the predominant variants that has gained a lot of popularity and a lot of vendor implementations is around photonic, especially around photon detection. A lot of things, that's what some of the testing NIST did, was focused on photonic and spooky effects at a distance. And also entanglement, especially if you're in the flavor of quantum key distribution, that really focuses on entangled photons being the root cause of the randomness, and we'll touch on that more in a second. There's also other noises like laser phase noise. And we can also then get into things like another big class is around electron tunneling, where the spin of the electron, because it's in superposition, can again result in an unpredictable result. And so great news as we continue to explore and invest billions in quantum devices for compute, we'll start to have more and more quantum materials or quantum styles that can be used as this root source of physical raw entropy. And this is a very non-exhaustive list, and it is not meant to either report or endorse or criticize anyone. It's just to give people a flavor that lets you know there are a number of vendors that are actively pursuing the commercialization of this technology, including a number of folks who are here in the room. I can spot some of our friends. There are also some of them who are here as sponsors of this conference, so please do seek them out and check it out. Interestingly, the majority, not unexpectedly, follow the more classic, I'd call it RNG model of a device that goes in a box and is locally present. And in fact, you can therefore get a FIPS certificate for that. In fact, QSide just got awarded their FIPS certificate for their hardware. So that's a fantastic example of new technology fitting in a certification box. But we also start to see cases where Quantropi and others are maybe stretching beyond the FIPS box a little bit in order to look at Entropy as a streaming service. Because especially as we look to say, can we take advantage of this technology while the sources are still expensive, relatively speaking, can we go ahead and still get advantage of that quantum entropy in brownfield implications until these quantum sources become affordable or deployable enough that they can be embedded in everyday device. You know, a price point today for a 1 gigabit per second entropy device is PCIe card with its own power supply is plus minus $8,000. So a power cord and a PCIe card and $8,000 is not going in my iPhone, right? But yet this iPhone may be being used for national security or banking or personal information, things that I want to protect. And so in some cases, this streaming model stretches 90C beyond its current definitions, but it's again is seen as a way to say, can we pragmatically make entropy available? And in some cases, there's some kind of very exciting synergies, because folks like Quantinuum are actually generating the random from their quantum compute. So it's almost like exhaust from their core quantum processors. QCI is a similar vein. And so it's an interesting point where, again, advances in quantum technology, besides becoming an attack vector against cryptography, they actually fuel at least one form of defense. And so again, very interesting advances as we move along. And so I did want to just comment on the general architecture of this idea of quantum entropy as a service, where we talk about usually generation, distribution, and consumption, a layered architecture. Again, nothing too tricky about it, but it's important, especially as we also start to bridge into physical environments, but also cloud, right? Because on-prem or in my pocket versus in the cloud, how can I have cryptographic keys, cryptographic entropy in all places? Because it's really hard to take my own proprietary hardware and screw it into Azure, right? And so maybe someday Azure will have this as a service, but do I want to wait for Microsoft to decide, and Satya to decide to provide this as a service, or do I want to have it now? These give the security profile folks a chance to have choices in where they get their entropy and what they do about it, and we'll see more of that in a second. The other domain, and this one is still even a little less explored, is pseudo quantum random number generation. So just like DRBGs are in many cases depend on and use a variant of symmetric algorithms like AES, we're starting to see quantum algorithms which are symmetric in nature being configured to be pseudo quantum random number generators that have periodicity, because all software-based entropy sources have a period, but have near infinite periods, but still have periodicity, so they're not as robust as a true hardware source, but they're software, so they can go places like IoT, but it requires use of new algorithms, and research into new symmetric algorithms is still, as always, an area where people tread carefully and slowly, because again, there's a long history, and then how do we get to the next generation of symmetric from here? So, but it's still a thing to think about, especially in offline edge or devices that don't have any possible true source available to them, at least not in the near future. And so that's a recap of the differences, so we don't need to do that, but it'll be available. So, of course, all these things are important that we're not ignoring, and even though it's new technology, it's still, in order to be successfully brought into the enterprise, successfully brought into the government, that it is finding ways to fit it within and source it within standards and with certifications, because that ultimately is how we can build confidence and know that it's a secure and appropriate product to have in the market. And so with the few minutes that I want to have left, I'll just do a quick survey of some of the different deployment use cases we're seeing with this new technology to give flavor for things people can do. And the first one is one of my favorites. This is a IETF standard, RFC 8784. And this basically says that if I have an IPsec VPN, I'm using IKE v2, if I mix a pre-shared post-quantum key in with a traditionally exchanged key, the new synthetic key or the new hybrid key is considered post-quantum secure, and I can then use that with AES. And what's exciting about this is an upgrade to your IPsec VPN that's standards-based, meets the criteria of the Quantum Cybersecurity Preparedness Act and is not dependent on any algorithm upgrades. And so that becomes pretty exciting because just by putting entropy, strong entropy, as a pre-shared key into the IPsec peers, I can now achieve post-quantum security. And in fact, NSA put out guidance on specifically the management, the patterns for management. Now, I can talk to folks and they say, well, if NSA's got their finger in it, hey, but that's, that's tinfoil time. But importantly, it's a design pattern that says what's good, because again, it's one thing to say I've got a key. The question is how did I get it? Where did it come from? Where did it go through? How do I make sure that I don't screw it all up by compromising the key on the way in? So the fact that NSA took explicit guidance on this exact solution set, and we've worked with a number of folks, but Palo Alto, Cisco, Fortinet, Juniper, Red Hat, all already support this in their GA products. Yet, if you talk to any of them, almost none of their customers have activated this functionality. In some cases, it's because the box itself has no strong entropy source on it. So that creates this window of opportunity to marry these two things up and use quantum entropy to deliver quantum security. And we've timed it from an end user saying, oh, I want to do this, to installing the tools, getting it set up and turned on, 5 minutes. So if you can say, I can upgrade my VPN to post-quantum security that meets federal guidelines and is an internet standard in 5 minutes, that's kind of low-hanging fruit, relatively speaking, from a security posture perspective. Another strategy is to start to look at actually injecting it below the operating system at the kernel level into the entropy pools of the underlying device. And in particular, this pattern is really strong for virtualized environments. And so a tip of the cap to Red Hat, because they actually published the guidelines on how to do this effectively. But what's important about that is that way, whether it's I have a device and I can slot it in to the core machine, or I can stream it in from one of the services, the net result is whatever OSs are running in the hypervisor inherit strong entropy. And because it's at the operating system entropy pool level, from the operating system on up, nobody knows it's there. Nobody knows that you've swapped in better entropy, and so it's not a change in version of the operating system. It's not a rebuild of any application. It's not new crypto calls or new calls to an RNG. It's there and just available. You've just improved the feedstock. Again, it's like going to the pump and putting better gas in your car. And we think that this is a model that, again, lets people get to a stronger position, especially if their current entropy sources are below that 0.85 threshold. And again, with a streaming model, you have this opportunity to then start to think about customer managed encryption keys, where again, it leads us to this concept we think is going to become very critical, right? We've seen, again, quantum attacks on software and other attacks on software supply chain, which is why that's what CISA is saying, that's the first use case we want to see go post-quantum. Well, people are going to start worrying about the supply chain of their entropy. They're going to start worrying about what we call entropy sovereignty. And if I'm in the cloud and I'm using SaaS, again, I'll pick on a different one, is Bezos, then AWS giving me good entropy, right? Because everything that goes in S3 by default is encrypted, AES 256. Thanks, Bezos, but wait a minute, what key did you use? Because what's the point of you encrypted it with a garbage key? And they'll tell me it's a good key, but do I know? I can't see it. And so the interesting question becomes, if I can now, and they all have it, every major cloud, every major SaaS platform already has a utility that allows you to bring your own keys. And so if you're going to bring your own keys, then why not bring a strong one that meets the entropy quality that you want, and now you've got entropy sovereignty. And we think, again, this is going to be, especially as you think about data sovereignty in the EU, we think this is going to be, again, a major topic where people are going to start to sweat, where's it coming from? Of course, a tip of the cap to quantum key distribution. This is kind of the OG of looking at quantum mechanisms for entropy distribution. And this one becomes, again, based on the entangled photons. Of course, the early adopters in this space are the telcos, because they're looking at it, and because it requires direct fiber connections, they've got them. That's why it's a good thing for them to deploy. An important point is that in the current implementations, it still requires a parallel classic channel, which, as of last month, hopefully is now being upgraded to using post-quantum cryptography. But there is a classic component to the real-world implementations of this, so that's always something to keep in mind. But again, it's using the power of physics to give us defense in depth. And since there's a physical version, we're starting to see people come up with digital versions using a combination of NIST PQC and AES. You can emulate that same behavior. And the great news is that for photonic QKD, as well as digital QKD, ETSI came out with a specification, ETSI 014, which is an interface standard so that you can interoperate. So I can mix and match Toshiba and ID Quantique, hardware and software. The good news is I can achieve both a physical and a digital extensions, because the physical ones only go over fiber, the digital ones can go over any transport mechanism. It opens the utility of this entropy distribution to more endpoints, which is the ultimate goal, because we want better key security. And this is a use case. This is actually one that came from a bank, where they were saying they have a team of their encryption and cryptographic security team, whose whole job it is synchronizing keys between on-prem HSMs and cloud, right? Because there's no secure manner to do it. So if you start to look at either photonic or digital quantum key distribution, that allows you to get a quantum secure synchronization mechanism that can be automated, so you don't have humans cutting and pasting, because that's likely to be fraught with operator error. And one use case that's been explored, at least academically, is looking at saying, if I'm going to do with 5G, where I've got gigabit and terabit backhaul, that the IV required for the symmetric encryption, again, there's been mathematical studies that said strong IV is an important contributor to AES performance. So if I can have a streaming source, in this case it was PQRNG because it's running on a phone as the source, if I can do it in software, I can now inject at really high rates, as much as 32 megabits per second per device. I can inject that IV, and as a result have the best performing security over that 5G network. So to bring it home and give us a couple minutes, landed plane on time, the great news is a number of the vendors I mentioned and a few other folks in the industry like Palo Alto are kind of coming together and saying, this is all great, but right now it's a bit the Tower of Babel, right? ETSI 14 for QKD is a uniform interface standard. If you look at some of the NIST certifications, they talk about a conceptual API, but there's no API specification. So we're seeing fragmentation between different vendors with what are the standard API calls, what is a common language, because so now every time anyone tries to use one of these brand new products, they have to create a wrapper layer or they have to translate in order to integrate. And the differentiation between products shouldn't be their API, it should be their core capabilities. And so it's in quotes because the working title, which may stick or may get written something cooler or whatever, is the Quantum Entropy Alliance. And this kind of informal group of folks has already started talking about how can we make kind of a universal API along the lines of ETSI 14. That one's specific to QKD, but one that's just entropy in general, whether it's a device level or streaming, what's a common API so that then developers can have a single interface. This informal working group has already briefed NIST once, and to start to put that on a track, I'm going to brief some of the other standards bodies later to see if we can get it into a standards track. Because again, the goal is by lowering the barrier to integration, we should increase the adoption of this new modality and therefore improve overall security. And since I'm a child of the 70s, the stolen clip art is of that era. So, all right, and so hopefully I left at least a few minutes for. Well, we'll see if the clicker is going to go with it. Oop. Yep. Right, and so that is a fantastic question. And generally speaking, the two modalities would be either through, if you're using quantum key distribution, then you do it through entangled photons, fantastic. If you're doing digital, you would do it through using current digital encryption to protect the payload in transit, right? And the whole, we had this conversation before, you almost get into a bit of a recursive loop, but the whole idea is that if I have a strong key and I can share it out of band, I can then, and I trust AES to be quantum safe, well then I've established a quantum safe connection between the two connections. And if I don't want to do it out of band, if I trust and believe in the NISP key exchange mechanism, I can use that as the mechanism to exchange that initial key. So as the algorithmic components are considered quantum safe, then that gives you the ability to do this in a way. If you don't believe they're quantum safe, then you might go photonic or you might not use this mechanism. That's kind of the hierarchy of beliefs.
Attacker who knows the encrypted file drops the entropy from, let's say, almost 1 million down to 256.
Well, so I would be happy to chat offline. I'm not sure if I followed in, because it depends on the nature, as you're describing it, the attack, and the question is how they would be manipulating the payload and trying to lower its entropy. The question is, what would they be able to do successfully in order to, so the question comes down to what's the attack vector and how is it successful at actually modifying the encrypted payload in the...
No, it's not a question of modifying. But if I would know, if an attacker would know the encryption key, then he could decrypt the file and learn 1 million random bits.
Sure.
That's clear. But if you have an AS256-bit encryption, this is only a 256-bit problem. Certainly practically secure. But if your whole file would have, at the beginning, 1 million bits of min entropy, let's say, then it would drop down to 256.
Well, we'll have to take that offline because I'm not sure I'm following the question, and I may be missing the point, so I don't want to get it wrong. So I will gladly chat with you, and I can try to see if I can answer it correctly.
And I have a second question, if time permits.
Yes.
Sure, please.
Concerning pseudo-random generators. You had another slide.
Yep.
Which kind of pseudo-random number generators do you have in mind? Because short periodicity or poor dimensional distribution, that it's typical for pseudo-random number generators that are not used for cryptographic applications, but for stochastic simulation for Monte Carlo methods. That means, but there is not a security requirement. They are usually okay for that. Linear concurrential generators, for instance. But if you think of, for instance, NIST proof designs, they also I usually call it deterministic, but it's another name for pseudo-random number generation, and then you do not find these weaknesses.
Yeah, I think that's a fair point, that there's, again, the periodicity depends on the implementation, and so short is a relative term, the idea being it's extended as long as possible, and the idea being that using new quantum algorithms would extend potentially, right, that's the research that can be done, extend the periodicity, and that's always a better thing. So that's really the intent of the point.
Okay, thank you.
You're quite welcome. All right.
So please join me in thanking Mr. Redding on his sharing on quantum entropy. Thank you very much. This closes things out for our second day. I think there's networking downstairs. You're welcome to continue that downstairs and then back tomorrow. Thank you all for coming and joining our sessions today.